So the last little section in 4.1 is called Enthalpy of Solution. So to recap what we've done so far, we've looked at Born-Haber cycles, which is a method we use to calculate the lattice enthalpy of a substance. And remember, the lattice enthalpy is the energy needed to break apart 1 mole of an ionic lattice into individual gaseous ions. What this section is about is actually using those values of lattice enthalpy, which you've just calculated, and actually working out something from them. The thing we learn about what we work out is the enthalpy of solution, which basically gives you an idea of the energy change you'll see whenever you dissolve something in water. By calculating the enthalpy of solution values for different substances, allows you to work out how soluble something might be in water, which might be something that's useful to you in whatever you're looking at. So we're going to look through how you actually calculate the enthalpy of solution using those lattice enthalpy values. But before we do that, we need a wee bit of background about what actually goes on when you dissolve something in water. So reading down on midway through page 7, an important use of lattice enthalpy values is in the calculation of enthalpy of solution values. This allows chemists to make sense of the varying solubilities of different ionic substances. So here's the two processes we're going to look at. Whenever an ionic substance dissolves in water, the two different processes take place are, first of all, the ionic lattice breaks up, and second of all, the water molecules form polar bonds with the ions. So what we mean there is solubility is something that happens very quickly and sort of instantaneously, but it's helpful if you think about it as two separate processes. So if I kind of show you with this 2D diagram down the bottom, comparing the left hand side to the right hand side, this is what we have before we dissolve something. We've got a complete ionic lattice, we've got irregularly lined ions all together, we've got water molecules in a beaker. Once we add the ionic lattice to our water molecules, we see two changes. The first change is the ionic lattice has split up, so we see all the ions are now separate from each other. And the second change is we've now formed new interactions between lone pairs on oxygen and delta plus H's with those ions. So we've got two different changes to keep track of. The first change about the ionic lattice breaking up we would relate to the lattice enthalpy, because if we're breaking apart a lattice into individual ions, that's pretty much the same thing as what the lattice enthalpy describes. We've got a new energy value though for the second part. The water molecules forming their new polar bonds with the ions. We've got an energy value called the enthalpy of hydration, which is just the enthalpy change you get when you form those new attractions between water molecules and ions in solution. So therefore, if we're looking at the overall energy change whenever you dissolve something in water, an ionic substance, you're getting this expression here. The enthalpy of solution is the lattice enthalpy plus the enthalpy of hydration. In other words, these two processes we looked at up here. So to go alongside that discussion, you've got two kind of new definitions here. The enthalpy of solution is the enthalpy change when 1 mole of a solute dissolves in water, and the enthalpy of hydration is the enthalpy change when 1 mole of gaseous ions are converted into 1 mole of aqueous ions. Just one more thing to mention about the diagram at the bottom that might be useful to think about. In terms of why some substances might be soluble and why some ionic substances might not be soluble, it really is the balance of those two factors. For example, breaking apart that ionic lattice is endothermic. It requires you to put energy into breaking them apart. But forming new attractions is exothermic, allows you to get energy out. If you've got an ionic lattice which is so strongly attracted to itself that the lattice enthalpy is huge, and you don't actually get that much energy back from forming new interactions, it's probably not going to be soluble in water because the lattice enthalpy kind of outweighs the enthalpy of hydration. However, if you've got lattice maybe that forms really strong attractions with water, giving it really big enthalpy of hydration, and the lattice enthalpy isn't too big to break apart, you will be soluble because the hydration enthalpy will outweigh the lattice enthalpy. So it's kind of those two factors against each other, breaking apart this lattice, forming new interactions, which determines whether something's going to be soluble or not. So with that background in mind, let's look at the wee calculations we do to calculate enthalpy of solution. You might be glad to hear the calculations for this bit, they aren't as complicated as Born-Haber cycles, but they're kind of similar in terms of their layout. They're based upon Hess cycles again. So again, if I do it from scratch, it might be a wee bit easier. What I'm trying to calculate is this change here. I'm going from an ionic solid, and I want to work out the enthalpy of solution. The enthalpy of solution is the energy change when you break apart that ionic lattice and dissolve it in water. So it's Na plus Cl minus. That might look a wee bit similar to what we had for the last enthalpy, but the important difference is state symbols here. These ions are dissolved in water, they're not gaseous ions. So according to Hess's law, if I want to calculate that enthalpy change, I need to find an alternative route from the left hand side to the right hand side. The alternative route I use is this. I look at the lattice enthalpy first, because the lattice enthalpy gives me the energy change going from the ionic solid to the gaseous ions, like so, which is very close to what we've got on this right hand side. And then all I need to do to get to my finishing point is work out the energy that I'll get out by taking those gaseous ions and dissolving them in water. So in other words, the hydration enthalpy for each one. The important consideration is that you'll have hydration enthalpies for any ions you've got within your salt. So there's two different values, one for sodium, one for the chloride ion here. So that's kind of what we get. So if we follow this cycle along this route, which we might have values for, we can calculate the enthalpy value for the one we're trying to calculate, the enthalpy of solution. You have kind of got an option here though. What I showed you is kind of the more traditional Hess cycle triangle kind of format. You might also see this kind of more Born-Haber cycle looking diagram. It is actually showing you exactly the same information. This is the solubility enthalpy of solution value you're trying to calculate. You go via the last enthalpy first to break apart into ions in the gas phase, and then you hydrate those ions. Maybe one way advantage of this cycle is it does show you explicitly that you've got a value for each ion here. In this diagram is only just 1 hour of hydration. Really important you remember that you have to have hydration values for any ions you've got in your salt, not just one of them. So if we look at the wee example here, just dive straight into the numbers. Using the enthalpy values in the table, calculate the enthalpy of solution of sodium chloride. So it gives you a table with the last enthalpy, which we need, and 2 hydration enthalpies for a sodium ion and a chloride ion. So I can draw out my recycle, either way, it doesn't really matter. Look in this left hand one, last enthalpy is plus 776. For sodium, the hydration enthalpy is minus 407, and for chloride, minus 364. So looking at my cycle, again, sometimes I have to be wary about flipping arrows and things like that. In this case, a wee bit simpler. The arrows are actually nicely aligned. I actually follow that route from left to right. I'm not gonna have to flip anything here. I can just add all those values up. So what I do for my sum at the end is just plus 776, plus minus 407, plus minus 364, type it in my calculator, and that'll get me a final value of plus 5 kilojoules per mole. So it's very slightly endothermic. So it is just applying those values to your Hess cycle, being careful with the calculation. Probably the one area we can get a wee bit tripped up on here is in hydration enthalpies. As we'll look at an example in a second, if you have things like CaCl2, you might need to double some values for chloride ion. So it'll be a wee bit tricky around here, but don't overthink it. It is just following that cycle and adding some numbers together. In terms of about the values you get, generally what you expect is if something comes out as being very exothermic when you dissolve it, it's going to be soluble because it's favourable to be exothermic. What you might notice here though is this is slightly endothermic. You might think that means it's unfavourable. In some cases, something that can be slightly endothermic does still dissolve because of what we call an increase in entropy. Entropy is a topic we look at in 4.2, so don't worry about that for now. But if something's going to be soluble in water, generally you're looking for a very large exothermic value or a very small endothermic value, then it might dissolve. But anyway, looking at our wee example here, the slightly trickier one. So same kind of style question, we want to calculate the enthalpy of solution. It's calcium chloride this time, and we got similar values given in the table here. So I'm going to start by constructing the same cycle as before. It's CaCl2 because calcium chloride. I'm going to split it apart. I want to find the enthalpy of solution. So it's going to split onto the calcium 2 plus ion in the aqueous phase and 2 chloride ions. Again, this always has to be balanced across the equation. I'm going to look at my last enthalpy first as an alternative route. That will split them apart into calcium 2 plus gas and 2 chloride ions. Gas, and then it said this is the bit we need to be careful about. Calcium 2 plus gas to calcium 2 plus aqueous is just the hydration enthalpy for calcium, so I can just plonk that on, minus 1650. However, I've got 2 chloride ions being hydrated here, so I need to multiply that value by 2 for the chloride ion to make it fit in my cycle. So 2 times minus 364. Again, the sum isn't that much more difficult. I am just following values. Sorry, I should put the last enthalpy on. Plus 2237. So I just need to add these values together. So all I get is plus 2237 plus minus 1650 plus 2 times minus 364. Again, just be careful with your pluses and minuses. Make sure you're not contradicting yourself. Giving you a final answer of minus 141 kilojoules per mole. So as you can see from the value here, it's quite a strong exothermic reaction, so therefore we'd expect it to be quite favourable for calcium chloride to dissolve. We expect it to do quite readily. We have that wee discussion just on the top of the last page, just what I mentioned earlier. An exothermic value for enthalpy of solution usually indicates a solid will dissolve in water. However, in some cases, solids with small endothermic values, even though you might think that's unfavourable, can still dissolve due to entropic effects to do with entropy. Don't worry about that for now, we'll cover it in our next topic. One final little bit of theory, similar to we had a wee bit of theory with the last enthalpy values, just in terms of explaining what's going on with solution. First thing is, you can sometimes get these strange questions where you're asked to kind of describe the attraction between your dissolved ions and the water molecules. So that can be in terms of a diagram. They can actually ask you to draw this in the exam, or maybe give a written explanation for it. It's nothing too complicated, hopefully. It's just describing which bits of which species actually interact with each other. So we've got a positive ion and a negative ion whenever you break up a lattice. It's important you realise that the positive ion will be attracted to the oxygen atoms of the water molecule, because remember that's the delta minus part, opposites attract. So the lone pair on the oxygen will have an interaction with the sodium or the cations in an ionic lattice. However, with the negative ions, the anions, they'll be more attracted to the delta plus H atoms of the water molecules. So that's how you should draw the attraction. So this is pretty good kind of model for how you should draw it. Just plonk your ion in the middle, draw wee lines, drawing to probably about 4 is a good number because it does form multiple interactions per ion, and that's how you represent it. In terms of writing, you just say, when ions are hydrated, interactions form between ions and water molecules. The delta minus oxygen atoms are attracted to cations, and the delta plus hydrogen atoms are attracted to anions. That's just all there is there. The final bit is just about explaining why your enthalpy of hydration values might be different from each other, because that's a little bit quite easy to explain. In general, enthalpy of hydration values are always exothermic. You're always forming new interactions whenever you throw a gaseous ion into water molecules. It's always going to be happy to form those new interactions. Obviously, the size isn't going to be the same in each case, so we need to explain why it might be different sizes. So first of all, explain why the enthalpy of hydration value for fluoride ions is minus 506, whilst for chloride ions is minus 364. Again, it's quite similar to what we looked at with the last enthalpies. The charge is the same here. Fluoride ion is F minus and the chloride is Cl minus, so there's no difference in charges. However, the size is different. What we probably use in this explanation is more of an idea of charge density. In fluoride ion, it's much smaller than the chloride ion, therefore the same charge is kind of concentrated in a smaller space. Therefore it's more concentrated, therefore it actually can form slightly stronger attractions. So all we put here is that the fluoride ion has a higher charge density than chloride. Might want to back that up, I would just say that's due to a smaller size. Therefore, there's a greater attraction, probably be specific about where that attraction is forming, to the delta plus H atoms in water, and therefore a larger enthalpy of hydration. Second example, explain why the enthalpy of hydration for magnesium is minus 1920, while the value for calcium is minus 1650. So the value for magnesium is bigger than calcium. Again, it's a similar kind of idea here. We've got positive ions. They're both in group 2, so they're both going to be 2 plus, Mg2 plus and Ci2 plus. It's going to be with charge density again. Magnesium is slightly above calcium in group 2, therefore it's a smaller size, therefore that charge is concentrated in a smaller area, therefore a higher charge density. So what we'd say here is that Mg2 plus ion has a higher charge density than calcium 2 plus, due to smaller size. Therefore, at greater attraction, again I'll try to be nice and specific, it's an attraction to the delta minus oxygen atom in water, and therefore a larger enthalpy of hydration value.